do that in a computer quite easy. You can jump from point to point to point easy because you can just adjust, you can call the name. You can also find your delta x. What also you could do is you could play around with different n. For example, let's say you're taking a integral of a function that you know how to do. Like, let's say you're taking a function like x squared or x cubed from like 1 to 2. You actually know how to take that integral, right? You do know how to exactly find the area for that, right? So you could do like, let's say this is square root of x, and then you're finding the area from 1 to 2, so you want to find that area. So you can actually do this integral and say, this is the integral root x from 1 to 2 dx, right? And find the exact area. So this would be A, you could call it the exact A. But then you could also write a code that does this root x from 1 to 2, and you divide it into n pieces. Now what you could do is you could pick n to be equal 10, you can pick n equal 100, you can n equal 1,000, and find the area associated with those. You could find like a of 10, a of 100, and a of 1,000, and you can find the area associated with how many n's you picked. All right, and then what you could do is you could find this difference between this area and the exact area. So then your error would be the difference between A and then your like AN. So you can actually figure out the error, and you can plot how your error goes down as your n increases. Because the more n you have, the more accurate your measurement would be. And so your error will go down as your n, so error goes down as n goes up. And you can actually show that using some plots. You can show that, hey, I have 4 or 5 or 6 different experiments, and as my n goes up, my error goes down. You can actually plot the points. And some people do a logarithm plot of it, so it's a nicer plot rather than just the plot of the point itself. You can play around with that idea. So that's the thing. Now, methods that you could use. The methods that you could do left-hand side, right-hand side, midpoint, trapezoidal, and all those stuff is in your notes, in your book. But essentially, if any point you pick, like let's say you pick an x star, essentially you are calculating the area of this rectangle. And the way you would find it is that this like A1 here is f of x star times delta x. And when you have 1, 2, n of those, then the total area is roughly the sum of I from 1 to n of f of xi star times delta x, so you find the f of x star is the height of that point times delta x. The next one is the next xi, so this is x1 star, this is x2 star, so again it's like somewhere here, so you add that, and then the next one would be somewhere here again, this is x3 star, so that's that. So you just keep adding these little pieces And essentially that's what you get, which if you take n to infinity, that defines the integral for you, all right? So if I were to do a numerical integration using MATLAB, first of all, you want to decide what function you want to use. So if you're writing a code for a project, I would use different functions. You could use like square root of x, or whatever that is. So you could try with different functions. So that's one thing you could, in your project presentation, you could say, oh, I tried this function and that function, and let's see how it works with, how it works with 3 different things. You can experiment left hand point, you can experiment right hand point, you can experiment midpoint, and you can actually have a presentation for each of those methods and say, by the way, left hand point or right hand point and midpoint, they all seem to be the same category when I do the error analysis on it. And so you could do error analysis for different methods, as well as the number of the n's, how many n's you have. So you could try n 10, 100, 1,000, 10,000. You'd also error analysis with the different methods, left hand point, right hand point, trapezoidal, all that stuff. Yes?
Is there a way to relate those different options with you know, like computational demand, so that you can look at error versus how much demand you know, because like if you can go bigger n, but then it takes more computational time.
Right.
Is it just about how many, like, you know, this minus this over this it does, or is it also, because like trapezoidal you'll need to do more math also, but it'll be like more accurate?
Trapezoidal is more computation and more expensive. We call it more expensive.
Okay.
Like you just have to put in, your program will run more to do one step versus, you know, a left hand point. Now, what happened is that any good programmer always thinks like the way you think. Like you think of how expensive is it to compute this. That's one thing. The second thing is, what is my threshold? Like, am I doing landing on the moon computation, or am I just doing a very simple problem like this? So depending on what your threshold is, then you want to be more higher end, more accurate, more work, you know. So for example, sending a jet up to space, you really want to be accurate. Otherwise, your millions of dollars will go to waste and just burn. So you double check it, triple check it, and you use n to the order of a 10 or 20 just to make sure you're dead on. And then if you're doing something much simpler, then you just do less n. You can try with different methods. So yeah.
Also, it depends on what kind of problem you're working on. I'm going to share a couple problems at the end where you have to use the trapezoidal method because, well, you don't have to. You can't use the midpoint formula in certain types of problems. So trapezoidal will give you much better data than an endpoint, and you'll see once we get there at the end.
I was hoping that that's what you're doing. I wasn't sure, but is that what you're doing, numerical integration?
Yeah.
Oh, perfect.
Yes, today's
perfect.
numerical integration.
So for my honors students, this lecture and the lecture are really important. If you're not in my class and you still want to do a project, we can work together on it, on just the numerical integration. What's important to me is that you try different things. You try different methods, you try different ends, and then try different functions. Now, if you're curious about some of these methods, try funky functions. Like try 1 over x, which is like this, right? And try to take your limit from like 0 to like 1 and see what happens here. Like see if you can work with that, or like try like 1 over like x to the power of like a third, and then go into limit and see. Don't like do simple functions, but then try stuff that when x goes to 0, you're gonna have it blowing up to infinity, but perhaps the integral of it will add up to a number. Do you remember the p-value test? So we'll cover that in our class soon, but you should have remembered maybe from your Calc 1. So anyway, if you have like a x to the power of third, I think that converges p is less than 1. And so you can try with different functions and see how you do. Question before I give it to Jordan? All right.